So calculus of parametric curves. Right, so the learning objective. So after this lecture, hopefully you can be able to determine derivatives and equations of tangent lines for parametric curves. You could be able to find the area under the parametric curve. Evaluate arc length of a parametric curve. Two main things, derivatives and integral. In derivatives, I'm going to learn how to find the equation of a tangent line to a parametric curves. And for integral, we want to find the area under the parametric curve and use the integral to evaluate the arc length of the parametric curve. Okay. Before we jump into formulas and whatnot, I want to give you some example and see what happens. A motivations example. What I would like to do is to determine the slope of the parametric equations. Of the line. And the equations are x equal to 2t plus 3 and y equal to 3t minus 4, where t is between -2 and 3. Right. So we don't know how to find the slope of the parametric equations directly yet. Right. But what we know that this is the parametric equations of the line. If we can turn these parametric equations into the form y equal to f of x, you can find the slope of the line, right? And you know how to find the slope of the line given y equal to f of x, right? So to do that, right? So first thing first, right? Eliminate t to obtain the equations y equal to f of x. If you want to be more specific, we can do like the equations of the line y equal to mx plus b. Right? If you want to be more specific, because the knowledge that we have at this point, this represents the equation of the line. Okay. All right, so let's eliminate the parameter t. So from x equal to 2t plus 3, we get x minus 3 equal to 2t. Then divide both sides for 2, you get x minus 3 over 2 equal to t. Right? Then you substitute t into the equations y equal to 3t minus 4. We obtain y equal to 3 times x minus 3 over 2 minus 4. Or this is equal to 3/2 times x minus 3 minus 4. Then you can distribute 3/2 into the parentheses. You get y equal to 3/2 x minus 9 over 2 minus 4. Or this is 3/2 x minus 17 over 2. Given the parametric equations, we can rewrite the parametric equations into the form of y equal to f of x. Right. And this form gives us then the slope of the line is m equal to 3/2. On the other hand, right, now if you just given the parametric equations, some complicated parametric equations that you don't know how to turn that into y equal to f of x, how would you be able to find the slope, right? So that's what we're looking for right here. So on the other hand, what we could do is you can take the derivative of the equations x of t and y of t. We can take the derivatives of x of t and y of t with respect to t. That is, right, so what we do, you have x prime of t, right, or dx dt. Right, so this dx dt means that you take the derivative of x with respect to t. Right? And the equations for x, let me write down here on the side so we have something to look at. Y is equal to 3t minus 4. Okay, so this is the equations given to us. Right? So I put that on the side. Now for the equations of x, I'm going to take derivative of x with respect to t. That means you take derivative of 2t plus 3 with respect to t. This gives me 2. And y prime of t, or dy dt, is equal to d dt of 3t minus 4, or this is equal to 3. Right. So it turns out that if you look closely, the slope, right, so m is equal to dy dx, right? So the slope of the line, dy dx, right, is actually equal to dy dt over dx dt. This gives me 3/2, which is equivalent to the slope found in the first bullet. So with this example, it shows us that, right, the derivative of y with respect to x can also be related to some parametric equations, right? So dy dx is equal to dy dt over dx dt. Right, so that led us to the first theorem here, right? Derivative of parametric equations. So consider the plane curve defined by the parametric equations x equal to x of t and y equal to y of t, and suppose that x prime of t, or dx dt, and y prime of t, or dy dt, exist, and assume that x prime of t is different from 0, then the derivative y prime of x, or dy dx, is given as, so dy dx equal to dy dt over dx dt. Or you can, if you want, you can write y prime of t over x prime of t. Okay, so let's prove this theorem. Hopefully this is a straightforward proof. We're going to use some chain rule that we learned in Calculus 1 to prove this theorem. Okay, so proof. So the theorem can be proved using the chain rule. So assume that the parameter t can be eliminated using a differentiable functions, differentiable y equal to capital F of x, right? But y and x are related to one another by the third parameter, or by the third item, which is t. So instead of writing y equal to f of x, you can write then y of t equal to f of x of t can be differentiated as Right, so we differentiate both sides of the equations. We get y prime of t is equal to, so when you take the derivative of this function, this is the composite functions. So this, let's take a quick note here. So when you take derivative of composite function, you have to use chain rule, right? Which the outer function is capital F, and the inner function is x. Right? So the chain rule gives us derivative of the outer functions multiplied with the derivative of the inner function. Or you can write capital F prime of x of t equal to y prime of t over x prime of t. But since y equal to f of x, dy dx is equal to f prime of x. Thus, dy dx is equal to y prime of t over x prime of t. So in this example, I want to find the equation of the tangent line to the curve x of t equal to t squared minus 3 and y of t equal to 2t minus 1. So this is a type of parabola, and the picture of the curve is given in this image. Okay, so again, what we want to find the equation of the tangent line. But in order to get a line, you need the slope and a point on the line. So to get the tangent line, first you need to find the derivative of the curve at the given point t equal to 2 to give you the slope. So the derivative of the parametric equations is, again, so the slope of the parametric equations is calculated as, so m equal to dy dx is actually equal to dy dt over dx dt, or you can do y prime of t over x prime of t, given that x is equal to t squared minus 3 and y of t is 2t minus 1. So y prime is equal to 2. And x prime of t, right here, is going to be the derivative of t squared minus 3, or 2t. And then you can cancel out the 2, and you're left with 1 over t. So the slope of this parametric curve is m equal to 1 over t. So this is a function with respect to t, but you just need to evaluate the slope at just one point, t equal to 2. So you substitute t equal to 2 and you get the answer for m. So since t is equal to 2, we get that m, the slope, is equal to 1/2. So you get the slope. Now you just need to find a point on the parametric curve. So to do that, again, you have the point t equal to 2. So you just substitute t equal to 2 into x of t and y of t to obtain the points. Then the point at t equal to 2 is, so x of 2 is equal to 2 squared minus 3, or 4 minus 3 equal to 1. And y of 2 is 2 times 2 minus 1, which is 4 minus 1 equal to 3. So you get the slope, you get the point. Now you can write the equation of the tangent line to the curve, to the parametric curve at t equal to 2. What I'm going to do is I'm going to use point slope form to find the equation of a tangent line. So from the point slope form, we get that y minus y0 equal to m times x minus x0. So m in this case is clear, which is the slope. X0, Y0 is the point on the curve. In this case, X0 is equal to 1, Y0 is equal to 3. So this is just the notations that I use. Sometimes you find the formulas in terms of y minus y1 equal to m times x minus x1. It does not really matter. It's just x0, y0, or x1, y1. It's just a point on the curve. So in this case, x0 is equal to 1 and y0 is equal to 3. So you substitute that into our formula and we get y minus 3 equal to 1/2 times x minus 1. And you move 3 to the, or negative 3 to the right hand side, and you get y equal to 1/2 times x minus 1 plus 3. So this is the equation of the tangent line to the parametric curve at t equal to 2. You can actually go a little bit further to simplify the equations a little bit. So to do that, you distribute 1/2 into the parentheses. So you get y equal to 1/2 x minus 1/2 plus 3, and this gives you 1/2 x plus 5/2. Again, this is the equation of a tangent line. What you see here is that you start with the point-slope form and you rewrite the equations and you obtain something called the slope-intercept form. That's it for the example. Let's move on to another concept.